In this lecture, we will discuss sidewall friction. Sidewall friction is the inclusion of the friction between the side of the ramp walls and the soil on either side. Note that in all previous calculations, we just consider abutment weight multiplied by coefficient of friction. But this just considers the soil below the abutment. And I'm referring to this as the normal friction along the bottom because it is both due to normal forces as well as what we've already taught in the suspended bridge design course. This trick of including sidewall friction is only needed to make greater than 80-meter standard abutments work, but can be included to try and make a custom abutment work as well, or make a design more efficient to ensure that your checks work out. The equation we will use to calculate sidewall friction comes from equation 3.24 in a thesis that I have attached or added in the bottom of the unit and linked as well. I've applied this equation to the entire side of the abutment, acting as one large anchor block. And we'll now break down this equation by term. So of course, capital F sub S is the frictional resistance in kilonewtons. We want to multiply everything by 2 because we have two sides of this block. And remember, we're thinking of the abutment as just one large block slide of the soil. We're not going to break it up into its components here. We're just considering its area, its sidewall area that has some frictional resistance across the soil. K naught is going to be the coefficient of lateral pressure at rest. It's also taken as 1 minus sine phi prime. And phi prime is the effective internal angle of friction. And remember, in our case, we're using 30 degrees. Gamma prime is just the unit weight of soil that we've used throughout this course and throughout our suspended bridge design course. And H and B are geometric properties that we'll go into a little bit at the end of this lecture, but H is the embedment below the soil surface, and B is the height of the embedded wall. Delta sub S is the angle of friction between the soil and the surface. And in the thesis, you can read further, this is taken as anywhere from 0.5 phi prime to 0.8 prime. So we'll take it as a more conservative 0.5 phi prime. And finally, T, or thickness, as it's told in the thesis, is actually the length of the embedded wall when we think of this geometrically. Now, some of the term values themselves are relatively straightforward, like the weight of soil. But because this is a one-size-fits-all type of formula developed in the thesis, the geometry can be a bit confusing. So I'll go into it a little bit. Here is a simple diagram just for our purposes here. And first of all, when finding the geometry of the friction area and embedment, we'll ignore the top 30 centimeters of soil. Assuming that this soil has been disturbed during excavation or maybe excavation spoils that are filled in and no longer compacted, we don't want to rely on its capacity for any active earth pressure at all. So from 30 centimeters down, we can take the average of the front and back embedments, here D front and D back, and this will give us our value H, which is our embedment into the soil. Now, in our case, embedment is actually equal to the wall height, or we can take this to be the same term: the wall height that is under the soil, under that 30 centimeters of soil. So H equals B, and our term from above will simplify to just H over 2. And finally, T, or what's described as thickness, and in our case is actually the length of the wall that is embedded. Can be found as just the back of the anchor to the front of the foundation. Now, this could change if you have a very specific geometric case, but generally speaking, it's from the back of the anchor to the front of the foundation, unless your foundation is completely out of the ground. But you can deal with that case specifically when you're making your calculations for a custom abutment. And finally, at the end of this unit, we'll have a couple practice problems to make sure that you completely understand the concept of sidewall friction and can correctly calculate it.